Today we're talking about the first law of thermodynamics, and that particular law states that energy can never be created and it also cannot be destroyed. It can only change form. This particular law is one that scientists are pretty set on. We've not seen anything that shows us that we can create energy or that we can destroy energy, that we can only change its form. There are a lot of different types of energy. Now in this particular chapter we're talking about kinetic energy and potential energy, but you also have heat energy. You've got chemical energy, you have energy from light, you've got electrical energy, you have energy from molecular motion, you've got energy that is stored in chemical bonds, and the author's actually going to get into some of these different kinds of energy a little bit later on in the chapter. But what's important to realize is that all the energy in the universe is all there's ever going to be, and it's all there ever has been. As human beings, we are not able to create it or to destroy it. We can only change its form. So we can analyze physical situations based on this particular rule. And I'm going to work examples 8.4 and 8.5 for you, but I'm going to work them a little bit differently than he does them in the book, because when you look at his calculations, they all make perfect sense, but I think that there maybe is a little bit easier way to think about what we're doing as opposed to the number of different steps that he shows you. So let's look at example 8.4 first. Example 8.4 says that a rock is at rest on top of a 121 meter high cliff, and if the rock falls off the edge of the cliff, how fast will it be traveling the instant before it hits the ground? And we're allowed to ignore air resistance in this. So if I draw a picture here, and I have a rock that's sitting up here, and I know that this cliff is 121 meters high, and what I'm asked for is, if the rock falls off, what's the velocity down here at the bottom of the cliff? Okay, so let's analyze this rock in terms of the energy that it possesses. Before the rock starts moving, what kind of energy does it have? Okay, remember, it's not moving yet. So at the top of the cliff, the total energy that it has is going to be equivalent to the same amount of energy that this rock has at the bottom of the cliff right before it hits. Okay, now once it hits, we have a whole nother ball game, because at that point some of the energy of the rock has been transferred to the dirt and whatever else it may hit when it's down there, because other things may start to go flying. So what we're looking at is the instant right before it hits the ground. So because energy has to be conserved, the total energy of the rock at the top of the cliff is going to be the same as the total energy of the rock at the bottom of the cliff. Now, at the top of the cliff, again, it's not moving up here yet, so all of its energy up here is going to be potential energy. It's not moving, so there is no kinetic energy. So the potential energy at the top is equal to what kind of energy does it have at the bottom? Well, the instant before it hits, there's no potential energy left. It's all disappeared. It's all been converted to kinetic energy. Because it's at the bottom, there's no height left, so that mgh, that h is going to be 0, so potential energy is gone. So the kinetic energy at the bottom is all of the energy that the rock has. So what that tells me is that the potential energy at the top is equal to the kinetic energy at the bottom, okay? Now, how do I express potential energy? Well, potential energy is mass times gravity times height. The kinetic energy at the bottom is 1/2 times m times v squared, okay? So all I did is substitute in how I calculate potential energy and how I calculate kinetic energy. Now, if you notice what happens here, I have an m on both sides. So that m drops out. This is real similar to the calculations we did with the car going around the curve. And we said it doesn't really matter what the mass of the car is, the mass of the semi, the mass of the motorcycle. It all comes out the same because the mass on each side drops out. Remember doing that type of calculation? I think it was module 7. So this same type of thing here, it doesn't make any difference what the mass of this rock is because it cancels out on both sides. So now I can just plug in for my remaining variables. So gravity is 9.8 meters per second squared, and the height is 121 meters. Then on the other side, I have 1/2 times v squared. So I can multiply 9.8 times 121. That's going to give me meters squared per second squared. I'm going to divide both sides by 1/2, and then I'm going to take the square root. Well, if I had meters squared per second squared, and I take the square root, that's going to give me meters per second, which is the units that I should have for velocity. And when you crunch all those numbers out, you end up with a velocity of 49 meters per second. Okay? So that was example 8.4. Now we're going to work through example 8.5 and use a very similar type of argument. Okay, so in this particular problem, we have a roller coaster that looks like this. We have our cars sitting up here. We are given that from here, and they give us the distance all the way to the ground. This is 113 meters. This next dip right here has a height of 22 meters off the ground. And then this next hill, which you'll notice is not as high as the first one. This hill has a height of 67 meters. Okay? So that's the setup. The roller coaster is pulled up a hill that is 113 meters high. It stops at the top of the hill for a second. So it has stopped. So if it has stopped, what does that mean? If it's stopped, that means it has no kinetic energy. Okay, so keep that in your head. And then it begins to roll down the hill. It accelerates to the bottom of the hill, which is still 22 meters above the ground. And then it begins to climb another hill, which is 67 meters high. Ignoring friction, and that's a really nice thing that we could ignore friction because that would make this complicated. What is the car's speed when it reaches the bottom of the first hill and when it reaches the top of the next hill? So what I am looking for is I'm looking for the velocity at this point, and then I'm looking for the velocity at that point. Okay? So how am I going to go about doing this? Well, again, you have to keep in mind that total energy of this car doesn't change. It's going to change form, but the total energy doesn't change. So the total energy at the beginning of all of this is going to still be equal to the total energy at the, I'm just going to say the total energy at the bottom. So the total energy at the beginning is equal to the total energy at the bottom of the hill. Well, what kind of energy does the car possess at the beginning of all this? Well, we said it comes to a stop real briefly, so that means it doesn't have any kinetic energy. So the energy at the beginning is all potential energy, okay? Then what I'm looking for is the situation at the bottom of this hill. What kind of energy does this car possess here? Well, obviously the car is moving because we're asked what the velocity is. If it came to a complete stop, we know enough about roller coasters to know if it stops down here, it's not going to get up the next hill. So we're going to assume it's going to keep going, right? So it's going to have kinetic energy here, but it's also still 22 meters above the ground. So it does still also have some potential energy. So on this side, we've got both potential energy and we have kinetic energy at the bottom of that hill. So now I can plug in what I know. So I'm going to have mgh for the potential energy here. I'm going to have mgh for the potential energy here. And this is going to be 1/2 mv squared for the kinetic energy. Notice again, in all three of these terms, I have mass. And so that mass will cancel out. And once that mass cancels out, I have all the other information I need to solve the problem. At the beginning, so you remember I've got two gravities and two heights, so you've got to keep in mind which side is which. The side is at the beginning. So at the beginning, gravity, 9.8 meters per second squared. And at the beginning, it is at a height of 113 meters. Okay? Now, at the bottom of the hill, gravity hasn't changed, still 9.8 meters per second squared, but now it is at a height of only 22 meters. And then I'm going to have 1/2 v squared left over here, okay? So once I do that, I don't want you to get confused here, that 67 meters is not part of my equation. So then when I multiply these together, I multiply this together, and then I'm going to subtract, I'm going to solve for v squared. I'm going to assume that you know how to do all that algebra. Once you do that, you end up with a velocity of 42 meters per second. Okay? So these problems really aren't bad to work at all if you just look at the fact total energy at the beginning and then total energy with where you are now. Okay? So now that we've done that, now let's look at what the velocity is going to be at the top of the second hill. So I'm going to erase part of this. The total energy that the car had at the top of the first hill is still the total energy that it's going to continue to have all the way through. So now I'm going to have the total energy at the beginning is equal to the total energy at the top of the second hill, okay? Well, at the top of the second hill, so the first half of the equation still looks the same as it did before, potential energy at the top. Now here, it's going to still be moving, so it's got some kinetic energy, but it has potential energy again because this hill is a certain distance off the ground. So I'm going to have the potential energy at the top of the second hill and the kinetic energy at the top of the second hill. Okay? So again, this is mgh. This potential energy is mgh. Kinetic energy is 1/2 mv squared. Once again, the masses all cancel out. And I just have to get the right numbers plugged into the right spot. Gravity, 9.8 meters per second squared times the height of 113 meters. So this part looks exactly the same as what we did in the first part of the example. Second part, gravity, still 9.8 meters per second squared. The height now, though, is 67 meters because we're at the top of the second hill. So this is 67 meters. And then I have 1/2 times v squared. Again, you crunch all these numbers through, do your subtraction, do your division, and you're going to end up with a velocity of, I need two significant figures, and that's going to be 3.0 times 10 to the first meters per second. I didn't mention significant figures in the first problem, but I was limited by two significant figures here and two significant figures in the gravity. In both cases, two significant figures here as well. So both of my answers had to have two significant figures, okay? So when you go through these problems, I think it's easier to kind of look at it all in one big equation and say, okay, here's the situation at the beginning, here's the situation at the end, what kind of energy do I have at the beginning, what kind do I have at the end, and then kind of plug all that in the same equation, work it all out at the same time. If you will approach those problems from that perspective, I think they won't be nearly as complicated as the examples in the book may make them appear at first glance.